In this video series, we will discuss how to evaluate limits algebraically. Let's begin with motivation. Why do we desire to calculate limits in this algebraic way? What's wrong with the way that we have been looking at limits so far? Well, first of all, we want to avoid graphing a function if possible. It's time-consuming, you know? And we aren't all artists, so graphing by hand can get, well, messy. And it may be difficult to interpret a limit from a messy graph. Don't get me wrong, the graphing method is really great for visualizing limits, understanding the concept geometrically, which is why we teach this graphing method to you first. But it's certainly not the best way to evaluate a limit. Another method I want to avoid if possible is the table method. Again, time-consuming. And I'll have to spare a few minutes to find my calculator because I am certainly not plugging in 0.999 into a function by hand. Not to mention that tables can be misleading. Under rare circumstances, yes, but nonetheless, I'm not going tabular unless I have to. And don't even get me started on the limit laws. That method is way too tedious. We need a way to evaluate limits efficiently, as in fast and accurate, without having to draw anything or use a calculator. And that's precisely what this new method of evaluating limits algebraically will do for us. There are a lot of different functions out there. So as you can see, limits are going to come in all shapes and sizes. Because of this mathematical diversity, there is a handful of ways to evaluate a limit algebraically, depending, of course, on the function that's inside the limit. Probably the most important thing to remember about evaluating limits algebraically is always try using direct substitution first. I'll go into more detail in twist number 1, but the idea is when you encounter a limit, try plugging in the limiting value. Direct substitution is awesome because you can find a limit in literally 5 seconds. But the bad news is it doesn't always work. And you will know it's not working because upon plugging in the limiting value, there will be a 0 in a denominator, which we all know is mathematical taboo. To be honest, most limits that you will encounter in your calculus class will not be direct substitution friendly. And that's actually on purpose, because coming from a teacher's perspective, we want you to show us something more algebraically exciting. So when direct substitution fails, you need to investigate the function on the inside of the limit more carefully. There are 6 algebraic manipulations that can be performed to fix the problem of the 0 appearing in the denominator. Knowing which algebraic manipulation to use takes experience. It will not be obvious to a beginner. Each of these different manipulations will be discussed in twists 2 through 7. Some of these manipulations are more popular than others, but all are fantastic candidates to test your real strength in algebra. Heads up, the twists in this group are notorious for showing up on exams. Now, there are some special circumstances that can come up from time to time when trying to evaluate a limit algebraically. These are rare encounters, but we still need to address what to do just in case they show up. I will get specific about this group in twists 8 through 12. In all my experience as a teacher and a tutor, I have never seen this type of problem go outside one of these 12 twists. Every instructor is different. Some will require you to know all 12, and others will hand select which twists they want you to know. In other words, it is important as a student to be aware of which of these 12 twists you are responsible for. That being said, a true master of evaluating limits algebraically will know them all.